Hello, everyone. I hope my video for the previous lecture um, didn't disappoint you guys. I know it cut off, and unfortunately, it was beyond my control. Something strange going on with YouTube, so my apologies for that, and I will try to do something better about it. So let me just double check here to try to start everything up. Okay, so for the syllabus, I'll just finish going over it the day the tomorrow during our first day or first meeting. For now, I really want to make sure I go over um the square root square. I mean, this is a very important lesson for you for all of us. I mean, it's the start of a lecture, and I just can't believe it just kept cutting off on YouTube. On my previous school district, I used it. I used YouTube Live a lot, and I would record myself in the lectures, and it would just upload very great. And now apparently YouTube is having a lot of issues. So anyway, so the square is square. So let me introduce you to this lesson, and then wrap it up. It won't be long. Sorry if there you hear my son in the background, but anyway, the square is square from informal to formal geometric thinking. So here's the warm activity. So let's identify and connect the vertices that form a square in each grid. So you have three coordinate grids, right? Also known as the Cartesian coordinate grid for some cases when you start seeing the X and the Y. Um, so here we're gonna call it the just the grid. So on the first one, if you look very closely, you start noticing that the leftmost at the bottom has a square, right? So if we connect the dots here, okay, right? We're not the best drawers, but we'll try to draw it, right? So in this case, we have a one for the side. So we have one unit of measurement. Then we jump from here to here. We have another one unit measurement. So we can call this a 1 by 1 square, right? For those of you in building trades and construction type of classes, you should have learned this even, everybody should have learned this since elementary. And why do we call it 1 by 1? Because, well, if you multiply 1 times 1, how many squares do we have? So this one has one square unit, right? One square unit, because it's literally one square. So now let's go for the next one, number two. If we look very closely, number two has at the very upper right corner, it has a square. Now this one has multiple dots, right? And sometimes you see that this software does this. Anyway, so what we have here, well, we count the sides, one, two, that's 2 units for one of the sides, and one, two, that's 2 units for the other side. So this will be a 2 by 2 square, right? And if we multiply 2 times 2, we'll guess how many squares we have inside this square. Well, we counted 1, 2, 3, 4. So this is already talking about what? So we have 4 square units, right? We have 4 square units. So every time we do this, what are we measuring? What are we measuring? So what are we measuring every time we do this? So this is an additional note that what I wanted to give you last time, and um, you start noticing that this is something that may happen as you keep doing this again and again. Because the other video I had to do it 10 times until I realized that YouTube is already being faulty here. So anyway, so now we have the last one. When we look very closely, this is a little rigorous. It's a little hard, but I'll give you guys some time to look into it. And if you look at it very thoroughly, you start noticing that neither of the corners have it. But if you look in the middle, there are 4 dots you can connect. So we connect these 4 dots. If we connect these 4 dots, there we have our square. At this time, we didn't do the little thing. So let's try one more time. Okay, so there you go. And if we count the sides, we're gonna count 1, 2, 3. So that's 3 on one side, and this is 3 on this side. So we know this is a 3 by 3 square. And again, if we multiply this, 3 times 3, we're gonna get how many squares do we have inside? 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 times 3, it is 9. So 9 square units, right? So anyway, hopefully you can answer this question by the first day of class. I know it's kind of late because it's already the evening by the time I post this video, but I'll go over it in class. So overall, the learning goals here is to recall the properties of geometric figures. So right now we're working with squares, but what other figure we seem to be working with as we work through the lesson? So what is another property? Not another property, but another figure. Now we may not notice, but there is another figure. So what is another figure we are seeing? Okay. Now the second goal here is to understand that the results from measuring tools can be useful in composing a conjecture. So when we use tools like rulers, protractors, and that kind of stuff, we can make conjectures about certain things, right? It's the same way how, like when we investigate, like let's say there's a criminal investigation. Yeah, I know we're going a little dark here already. But when there's a criminal investigation, right, we need to ask questions, and based on what we receive in response, that's how we make a conjecture and a determination whether or not we need to go further, right? We have to escalate, or you know what, maybe we have to close the case. It just depends. But anyway, so however, they are not acceptable form of mathematical reason to validate conjectures. So unfortunately, using these such tools may not be the best way to prove something in mathematics. Mathematics requires us, to, after all, to use things we already know that's been established that we can prove by drawing and writing the some equations and um, just from based on that kind of work, we can make mathematical conjectures. However, um, one's considered informal, the other one's considered formal. We'll go more into that as the class goes by. Now, the last learning goal here is make a geometric conjecture and use mathematical reason to validate. So, again, we may need to use rulers, protractors, and other a compass to make angle measurements. I know we don't have those materials. It doesn't seem to be very much available, but if you use like the OneNote, there is an alternative to this. So hopefully you guys decide to use your computers. I know a lot of you have iPads issued by the school, so I hope you use this in constellation to your phones, right? Because now the phones are technically illegal because of the new state law. So hopefully we'll talk more about this on Monday in our first meeting. So anyway, so the essential question. So what based on the question I posted earlier, what other figure do we see to be working with, right? That's another question I just want to keep throwing at you as we go on. You have reasoned about lines and shapes in earlier grades and courses. How can you apply formal geometric reason to what you know? So let's go to the next slide for now. Okay, try to sketch a perfect square like the ones shown without tracing or using tools. So if you draw a square, right? I mean, hopefully you're using uh, erasable pencil or pens. So if you draw a square, okay, so there's a square. So if you use the software, it'll make a perfect square. Um, doesn't matter. We don't know what are the side measurements, but this is just what we call a perfect square. So, all right. So let's see what's in the next part. So, explain how you could decide whether one square is closer to perfect than another. Use your criteria to judge your and your classmates the square. So, what do you notice? And now list some properties of squares. So those of you who already did and may have already discussed and watched this video before our first day of class, so consider this. So what do we know about squares? So all sides are equivalent in length. So that's the first one we all should already know. A square has equivalent sides, right? And then sometimes they don't like to say equivalent. We like to say the word in geometry called congruent, right? It's just another fancy way to say uh, equivalent, right? Congruent is another thing we like to use here. So what's another condition? Well, we notice that a square has what? Well, two sets of opposite sides. So there are two sets of opposite sides. Okay, so that's condition number two, or property number two that we made write down. Okay, I don't know how you guys may write it, but just keep discussing. So what is the third one? Okay, we talk about sides, equivalency, two opposite sides, two sets of opposite sides. So we know this one's opposite this one, this is opposite that one. Okay, what's the other one that you may know? So you may notice this little square, right? I'm not, they're not perfect square, but I mean, it's something we use. So we know that all four angles inside the square, so all four interior angles are perpendicular. Or you can say are right angles, right? Right angles. Or you can say just 90 degrees. Whichever one of these is perfectly fine, right? It just depends how you work, right? So there's that other component in geometry we're gonna see a lot. We're gonna have to write a lot. And like in writing, it kind of gets us better in our English classes, right? Because we have to write there a lot. In physics, in chemistry, all these classes you're taking right now, you should be writing, right? That's how you make the content more relevant. This class is not just a 1 plus 1 is equal to 2, or solve for x, and there's your solution. Then let's close the book and move on. It shouldn't have to be like that. So expect that to be something that it's normal in our classes. So we'll talk more about that as we go on. And there may be more conditions or more properties, but I'll leave you guys to work on that. Okay. Let me just move on a little bit more. Okay, so we've done this one. In a way, mathematical reasoning is not different from scientific reasoning. In mathematics, you come up with educated guesses and test them to see if they're connected. You can experiment with different patterns and consider arguments about mathematical statements. And like other sciences, mathematicians gather evidence and become more and more confident about a statement when they obtain more evidence for it. However, in mathematics, a statement is not true or false until it is proved to be true or false. So um, we need to keep that in mind. Just because we learned that something might sound true, it doesn't necessarily mean it is. And because of that, we are required to look and explore, and hopefully we can recall properties that we learned in this class about figures, and we can make a conjecture, a formal, right? And if it's true, then we got to prove it's true. And then if it's false, we got to prove that it's false, right? And vice versa. So now for this next section, consider the diagram composed of three adjacent squares. So here's the one that we're using. So draw segments. So every time we see this symbol, the little line on the top, and you see two letters, it's talking about a line segment, right? So draw line segments AG, AF, and AE. So the way that's gonna look like is like this. So from A, right? From A, I like the way it looks. Okay, so from A to G, from A to F, from A to E. So those are your three line segments. I'm not a perfect drawer, but it's something similar to what you need to start seeing. So there's our segment. Use a protractor to measure angle A, B, and C, and list the angle measures. So this is very vital. This is very important, right? And again, I need to go to into our use of tools, a compass, a protractor, or if you're using the OneNote, hey, that's fine. You can use that. So if you click right here on the OneNote, depending which version you have, you should see this ruler. This ruler will be your compass or your protractor. So I'm gonna click on it, and then by pinching it or extending it the on the little pad, it can already give you the angle. So right here, it's already giving us that this angle right here, this angle right here is 45. And by the way, this angle here, according to the text, angle AGH using A. So AGH, this is angle A. So angle A is equal to 45 degrees. Now AFG, AFG, that's going to be called angle B. And then AEF, that's going to be called angle C. Okay? So now using the protractor, so got this here. Let me measure the other angle. So again, if you pinch it or you extend your fingers, you can modify it. And we notice that this one here is about 27 degrees. So let me move this. Okay. Now let's do the other one. So we notice that this one is about 18 degrees. Okay. So there's our angle measurement. So angle measurement of A is 45 degrees. Angle measurement of B is 27 degrees. And angle measurement of C is 18 degrees. Now, for the next question is compare your measurements with your classmates' measurements. What do you notice, right? So when you have this argument, what do you guys notice as you are? So now to get rid of this ruler, just click here. So now, something else I want you guys to notice is if you add angle A, angle B, and angle C, what do you notice it's equal to? Or what's close to? What number? So I want you guys to figure this out and notice something funny, okay? So making conjectures. In the previous activity, you may have noticed that the sum of the measures of angle A, B, and C is close to or equal to 90 degrees. Jada made a conjecture about the sum of the angles. The size of the squares doesn't matter. Given any three adjacent congruent squares, if the diagonals are drawn in the same way, the sum of the angle measures will always be 90 degrees. So again, here we have a diagram of our previous. So without measuring, do you think the size of the squares will affect the sum of the measures of angle A, B, C? Explain your thinking. Use a protractor to test your prediction and use these differently sized squares to record your results. So this is for you guys. And then for the next part, there are many ways to verify that the sum of the angle measures could be 90 degrees. Experimenting with different methods and visualizing are important tools that mathematicians use to approach problems in effective ways and gain confidence in their conclusions. Copy each of the angles A, B, and C from the diagram onto a different piece of patty paper, which we will not use to discuss. How can you manipulate the three angles to show that their sum is 90 degrees? So we'll talk more about that. So ultimately, from these two slides, we'll stop here. If you start making, this is what we call auxiliary lines. So the question I want to propose to everybody. So regardless of the number of consecutive squares, will all uh, angles produced by such auxiliary lines be equal to 90 degrees? So that's the question I want everybody to think about uh, when not having class or whenever you watch the video. If you do this, I just really do appreciate it. And again, we'll talk about 1.3 later. But again, at first, I want to talk about the syllabus. So once again, my name is Mr. Luis Alceda. You can call me Coach Sauce. That's fine, because of my last name. You see the word sauce, and you can just call me Coach Sauce because I'll be coaching after all. And in addition to that, I am very happy to be your teacher. Just to let you know a little bit about me, um, I'm originally from Brownsville, Texas, and I taught in Brownsville. Matter of fact, I taught at Porter down there, and then from there I taught the Austin area. I came back to the RGV. I started working in the Donna and Westaco. I also work for the IDEA Public Schools, so I have a lot of experience on me, and hopefully, it's very beneficial for you guys, my students. But anyway, we'll talk about the syllabus in class because again, the YouTube, my YouTube account that I wanted to use, for some reason when I live record my sessions and then record them and try to upload them, it just cuts it off for whatever random reason. So I'm gonna have to make the videos before and then just upload them that way without using the YouTube format. So anyway, I hope you guys learn a lot, and I hope we continue learning. Okay, so I see you Monday.